Okay, well, I see it's the top of the hour, so I'll get started. Um, Welcome, everyone. It's lovely to see everyone today. Today going to be something a little bit different. I'm going to talk about some literature. Nothing particularly earth-shattering, I suppose, but it's literature that kind of caught my eye. Um, let's get into it. And if you saw the spam, you may have seen my abstract. I always include it in the talk. And so, for some context here, I've been keeping up with the literature. It's a habit that I got into in my graduate school days. In my research group, each of us was assigned a journal and or two or three, and we had to kind of scan the journal for articles that were of importance to our group. And what I found is that there were a lot of articles that were actually kind of just of random interest, in addition to being important for the group. Um, so, you know, being an older guy, I write things down. I really learn much better by writing things down. Here are a few of my notebooks. I've got a bunch more. This happens to be in my work office, and I have a range of eclectic sort of interests, which I'll go into in a second. One of them is like chemistry and arts, and you can kind of see some of the pottery that I've painted over the years and had fired social events sitting on that table. Um, the I have no artistic ability, so I just paint the surfaces with like chemistry symbols and structures and things. So, so um, I was going to talk to you a little about a couple of papers that have to do with chemistry and art today. Um, so no, my current journal scan list, it's maybe a little bit larger than I should have. I'll put links and stuff in chat. My old standbys, I usually go for American Chemical Society journals. So like Journal of the American Chemical Society, it's their flagship. Inorganic Chem, Organometallics, those three get increasingly specialized, and then analytical chemistry. Um, and some more broad-ranging stuff, chemistry reviews, accounts of chemical research, and something that's emerged as a favorite is the Journal of Chemical Education. And more in recent years, online journals have started. Things like ACS Central Science, ACS Omega, ACS Electrochemistry. If it's got an ACS at the beginning of it, it's probably an online journal. We've got Catalysis and Earth and Space Sciences as well. And in the chat, I put um, the URLs to access those particular journals. Though open access ones are particularly nice. Not everything in those journals is hardcore um, hardcore research articles. They have perspectives and more newsy news things in addition. Right? Do I keep up with like my own work? Yes, of course. I can set search engines to send me lists of articles that are tailored towards my actual research, and I do that. I get a few articles that way each week. But by letting the computers do the searching for you, you kind of miss something. You kind of miss um, the randomness. Kind of like, oh, look at this paper. I have no overlap with it, but I am interested in it, right? So the randomness or serendipity. Um, So, things I look for, anything, for my research, anything with a metal that's like iron or ruthenium with NO attached, especially electrochemistry. Um, let's see, I should turn on my pointer. There we go. Um, and things that I look for, nitrogen fixation. I have an interest in that because the world could do with a better way of taking nitrogen from the atmosphere and turning it into fertilizer and things like that. Um, Augmented reality, virtual reality in chemistry. Surprise, surprise! If we're here now, then we have an interest in those things. Um, Arts and archaeology and educational articles on chemistry. Excuse me, and the LGBT community. So that's kind of like what I look for most of the time. Oh, and that's that's a few of the things I have in my office. Another pot. Um, that's from the St. Louis Art Museum. It looks like molecular models, but it's really just kind of a toy. Some Frank Lloyd Wright windows, and a big old magnet that my dad gave me when I was 7. So, for reference, that's 51 years ago. And let's see, that's as ancient then. It hasn't changed its appearance very much. So, um, s- so just for some context, I am interested in chemistry and art. I've taught 2 classes on it. Oh wow, 20 years ago. I don't get the chance to kind of teach the interdisciplinary courses and the honors courses all that often. I'm usually either teaching fourth year inorganic or the graduate level inorganic or the giant freshman chemistry classes. But I do have some instrumental classes that I teach, and one of the things I show is the use of this Raman microscope, and that's basically a tool to look at what's called the vibrational spectrum of a microscopic part of a sample. So here's a sample. It happens to be a 1 centimeter by 1 centimeter inkjet printed magnet that I got, 25 years ago at a Van Gogh um, exhibit at the St. Louis Arts Museum. It was in the gift shop. I did not like run off with it or anything like that. And I think I got like 50 of these little magnets. So when you pop it under a microscope, and this would be with a 50 times objective down here, plus the 10 times magnification up here. So that's a 500 times magnified image. It looks all splotchy. And it my joke here is that, oh look, if you zoom in enough, it's pointillism. So there's a bit of an irony there. Um, the microscope is wonderful. You can stitch together a bunch of images. This happens to be 14 images from from that. I'm not sure. I'm not sure exactly where it is. I think it's like above his eyebrow or something like that. So, um, yeah, it's an Olympus microscope, so it's a heavy duty microscope, and it's got lasers and things like that. So it's all kind of fun. Um, Moving on to one more slide, I'll show you what this thing does. So, um, I zoomed into that particular region, and I think the blue spectrum down here is from this point, and then I tried another point up here, and it pretty much gave me the same sort of spectrum. So, what we're looking at is it's a vibrational spectrum. I won't get into how Raman works in this particular talk, but we can clearly see some data, clearly see some fingerprints as to what is this particular dye is doing here. So it's like, yeah, this is funny. Um, we can get information non-destructively about samples. So I think that gets me to one of the papers I wanted to talk to. Yeah, so here's a fun paper. So let me uh, let me put a link to that in the chat. That one, this particular one is not. It is behind a paywall, so apologies for that. It's not the open source, but it's probably not a bad thing for me to talk about then. Make it a little more available. So Li Krong Wang from Brown University in Providence led this team, who's the corresponding author on this particular article. It's from Journal of Chemical Education. And it's talking about a lab activity that was part of a broader um, course, right? So we're talking about single activity in that course. And it took a little bit of one period, maybe about half an hour in one lab period, plus another 2 hours in the subsequent lab period. Essentially, what they did is um, they looked at how firing temperature affects the color of ceramic glazes based on copper. So, of course, copper-based pigments are historically significant. We can think of things like Egyptian fence for the historical significance of those. In this particular activity, students prepared and analyzed their own glazes. Um, yeah, Phil, I actually have a few more things to say about Raman later on um, in the second paper that I'm talking about today. So interesting. Moving on. So, what do they explore? And of course, you're going to see pictures of me and my cats. And here I am with Marduk. That's one of my cats. And we're discussing exactly how we were going to approach this talk. Um, she wasn't impressed. She's not impressed by much. So, what are they exploring? How does the color and texture of the final product depend on the glaze composition, the firing temperature? That was the key focus of this article. And the firing time would also be a variable. A- And since this was an interdisciplinary course, that was maybe not targeted at STEM majors, maybe targeted at a broader audience, some of whom may not be all that interested in, the numerical side of science, right? How can we connect to classroom concepts? There's the historical significance, and there is the actual objects that the students were able to make during the lab, and the sciencey part because it is a course. Look at the phase changes during the firing process. Look at the basic transition metal chemistry and how electron transfer reactions affect the final color. Look at, um, look at the actual analytical methods, X-ray diffraction, UV vis, electron paramagnetic resonance. I'm not going to bore you with details of EPR today, but maybe a couple of words about UV vis and X-ray. And of course, moving it back, having reflective writing in the lab reports as well. So, right. So I've recycled a couple of slides. I did a talk on color about a decade ago. So here's one of those. Um, let's let me if you wanted to look at some of these images, I've got them in the chat right now. Historical significance, fans, the Egyptian blue. It was the first synthetic pigment. It's a calcium copper silicate type compound. It's beautiful blue color. And the source of copper in later times is probably bronze scraps, and because later examples have traces of tin found in there, and kind of interesting. This recipe kind of fell out of favor for a couple of thousand years, eventually, probably, and has been recently rediscovered. This beautiful Wikipedia article on it in in the Wikipedia. This image is from the British Museum. No, it's from the Metropolitan Museum of Art. I do have some British Museum stuff later. Um, so, in this lab, they talked about, copper as a colorant, and I've added a little bit more. Some of these images aren't from the paper. Here's a picture of a rock. Yay, rocks. Um, the blue is called azurite, and it has the structure on the top left, and the green that you can see kind of on the surface is called malachite. It turns out azurite will turn into malachite on exposure to air and moisture. So as long as the rock is kind of buried or kept in a um, humidity controlled environment, um, the malachite doesn't replace the azurite. But you can kind of see the striking colors. There's the blue of the azurite and green of the malachite. Same sort of green. It's a copper carbonate. Same sort of green that you would see on the top of buildings that have copper roofs. The copper in the environment turns into builds up a layer of copper carbonate. Um, the malachite has a pretty simple structure. It's basically got a copper in, let's say, the XY plane, because this is three-dimensional. Let's say that there are four carbonates attached in the XY plane. So like if you're drawing this on a sheet of paper, you would have your copper in the middle, three or four oxygens, each from a different carbonate um, in the plane of the paper. And above and below the plane of the paper, you'd have an OH minus hydroxide. The azurite has a much more complicated sort of structure. There's a lot more bridging that's going on that you can see in the piece that's shown here. And essentially, there's less of the hydroxide around. And what happens when this stuff hits water is that some carbon dioxide is given off. The carbonate acts as a base, um, and we get a little more hydroxide forming. So it rejiggers its structure to become this one. But you know, we can see what colors copper is capable of. Okay, so we've got all sorts of blues, Egyptian blues, copper based. Prussian blue is not. It's iron based, and over the years, indigo, of course, is purely organic, and the newest one is the yttrium in indium manganese. Blue. And these colors are just representative of, you're not going to see the real color of any of these based on what a monitor can do. My monitor would give a different kind of color blue, but relatively speaking, they're pretty close. Okay, I think back to the paper. What did these students do? Well, um, they had to have a control, and so basically what they did was, hmm, I have a slide out of order. Let me go on. There is what they did. So the basics. They got clay from a local supplier. That's a quote from the paper. Local ceramic supplier. It's probably a kaolinite type clay, and the students made discs out of the clay in their first 30 minutes of this, or beads. They might have made tiny little beads by using molds. These objects were fired in either a high-tech furnace or in a microwave kiln, a much less expensive thing that might be available more readily to like a high school. So they were fired by the TA or the instructor. This kind of would take heating up slowly for a few hours to, I think, about 1200 degrees, and then, um, oh, um, yeah, and then allowing them to cool down. Um, and that would give a very porous um, uh, state called a bisque. Um, and you can paint on the bisque with the glaze mixture and then fire it again. So during the second period, they have a colorless control made up of these things: Gerstly borate, naphthalene cyanite, flint, flint and silica, 7.6%. The silica is really important because that's what makes it glassy, and 2% Edgar plastic kaolin. I've seen people make glazes from very dilute, um, I guess more of a slip sort of thing, very dilute clay. So you take some of the clay that you're using and mix it up with water, and then you can dip your um, object in it, and that, when fired, can also function as a glaze, right? So they made the base mixture and they used that as a control, and then they added colorants, right? So moving back one slide, down here circled in red, those are the four ingredients. They weighed out their ingredients. They made the basic glaze, and you see this is circled in red. That's um, that's where they painted on their disc, the bisque disc that they had made a control. Um, then over here, they made a mixture of glaze with 1% copper oxide. Over here, they made a mixture of the glaze with 1% malachite. They actually made the malachite in a previous activity. So this wasn't something scraped off the top of a famous building or anything. And then um, in the last one, they made a 1% silicon carbide. There should be capital C there, and 1% copper oxide. And kind of they pop these things into onto the disc, and in this case they fired them in a furnace. Let's see, and that's where we were before, and that's okay because we're gonna go past that. Um, so yeah, so basically, just what is a ceramic glaze before I get into what they found. It's a layer added post firing, right after you've got to the bisque, to form a glassy, non-porous layer on ceramics. So if you've ever kind of picked up like a ceramic tile, something you might use for a bathroom tile, on one side it's very smooth and shiny. On the other side, it's kind of rougher and more porous. Well, one side is glazed, one side is not. So that's essentially the difference. Um, the silica is very important. That's SiO2. I think quartz. If you get that hot enough, if you paint it on with as a water solution, but at 1200 Celsius, the water is long gone, and in fact, the silica starts to melt into each other and melt into the clay to form this nice layer. And you get a cross-linked tough surface. What do I mean by that? right? And of course, there's another cat, and she's in her dodecahedron, right? Another platonic solid instead of a cube. So cats also, don't discriminate on the basis of shapes. So this is what they found. So at room temperature, the various splotches look like that. Um, Sample was heated to 250 degrees. A little bit of drying, not really too much change. Maybe the silicon carbide thing looks a little, or that's a silicon carbide. Maybe the malachite looks a little bit more. Oh, that's a silicon carbide. Looks a little more dark, a little more heating, not really that much happening except maybe some darkening. But at about 850, you see the blue start to happen, especially with the second and the fourth samples. And finally, at about 1,000, um, the blue starts to get a little paler to my eye. And the silicon carbide copper oxide mixture doesn't look as if it's doing too much. I think these guys are the copper oxide and the malachite, and they are pretty much doing the same thing. I'll show you why in a little bit later here. So, um, the chemistry that goes on during the firing of clay, and this is not in the paper, this is, the value added by Mike. Um, the aluminosilicate planar layers, and I'm not showing you the whole plane because I drew this and you know, the whole plane would be beyond my drawing capability. Um, the aluminosilicate um, layers join together into a cross-linked 3D structure. So you might have in some clay like aluminum with OH groups aligned near silicon with OH groups or other aluminum. It doesn't really matter. But basically, the two OH groups attached to a metal, um, if heated enough, can spit out a water, right? So part of the water comes from one side, maybe up here, the OH, and the H comes from down here, and you're left with a bridging oxygen. This is what I mean by cross-links. These two chains that I've shown you are now linked together, actually in multiple sites. So if we think of, um, like planes that could slide against each other like pages in a book, but then we glue the pages together. That makes a solid, more brick type thing. Ah, brick. We're talking about ceramics. Said brick. Huh. So here's an example of a clay, Mont Mor Morillenite. And I was trying to like import a 3D structure of this using some new things I found out about Blender, but I'm not quite there yet. Um, I, so I still need to work on that. So essentially what you can see is there's a silicon, aluminum, silicon sheet. All of the silicons and aluminums are bridged by oxygen atoms. Then there's these calcium ions, like peanut butter in between the pieces of bread. This I guess is kind of like a Dagwood sandwich here. Um, the you know this is fairly malleable. It's a clay. The layers are going to slide against each other, means it can be easily shaped. Montmorillonite is actually fairly important because it has been used industrially for a long time. You can replace those calciums with other things, and then use the resulting materials like for cracking of hydrocarbons. And in fact, this the layers are so hygroscopic, like they absorb water so much, they actually expand when this stuff expands a lot when it absorbs water. Um, In fact, it can be used in the place of explosives to apply pressure selectively, like during building demolitions, when you basically kind of need like a slow levering open of a particular area. So, um, this is like the typical example of a clay that I think of. Let's just talk about what copper is doing. Hey, here's copper. When you dissolve it in water, it gets six waters attached, and it tends to have copper 2 plus tends to have two of the waters at a longer distance than the ones that might be all in the same plane, right? And this tendency to this ten this ends up being very light blue. Um, this tendency to have longer distances here carries over. In the paper, they say that the copper, when you copper oxide, when you fire it at 1,000 degrees, um, becomes a square planar structure. So it actually loses the things on the top and bottom. Not quite sure I 100% believe that, but I'm not going to gainsay that. Um, and so essentially, we change the electronic environment of the copper, which is going to give the material a slightly different color. Right. So again, these are actually from a lab that I taught. I don't have the hexaqual copper. It's so pale blue you can't see it. But like what we did is we added progressively more ammonia to the solution. Copper really loves ammonia, and as you add more and more ammonia, you get darker and darker solutions. And yeah, so here's my panel of cats. Uh, Over the years. He's still with us. Everyone else has passed away. Um, well, most of them had very long and happy lives. But yeah, uh, everyone, all the other cats in the presentation are alive though. They haven't met Schrodinger. All righty. So students also did some fun stuff because it's an interdisciplinary course for non-majors. So they were able to fire and glaze some of their own things. I think the fish is my favorite. I think the before and after of the fish really shows what the students were able to do. So that is actually from the paper. So what's going on here? Well, I said the malachite was prepared by the students, and essentially, when you fire the copper carbonate, you get copper oxide, and carbon dioxide comes out. So the malachite here, you see on this scale, progressive temperature increasing as you go down. At room temperature, they had the copper oxide. Copper oxide's kind of black, malachite's kind of green. Um, in this range, above the boiling point of water, you get water driven out of the sample, maybe around 500, 450 or something like that. More water is coming off, but you get this process here where carbon dioxide is coming off. So essentially, the two samples should become pretty much the same, right? It's all copper oxide. You might have slightly different particle sizes, agglomeration sizes, based on what you started with. All through this, there's outgassing of water, and the copper oxide starts to get um, um, absorbed into, coordinated by, becomes one with the glaze. And finally, we have above 1,000 degrees glaze with coloring. So you may be wondering, why the silicon carbide with copper oxide? What was the point? Well, the point there was the silicon carbide was supposed to be a reducing agent. See, copper oxide is copper 2 plus. Right? Malachite with a copper carbonate is copper 2 plus. And no reducing agents, you end up with copper 2 plus. A reducing agent gives an electron. So if you give an electron to copper 2 plus, you get a copper 1 plus because the electron has a negative charge. So copper 1 plus looks very different than copper 2 plus. And I've got a few slides on that. Um, oh, okay. So I will get to copper 1 plus. Just thinking about the temperature, you know, technically they would have been making earthenware if they're below the um, 1200 degrees Celsius. So they were using probably a pretty high quality clay to begin with. Um, so things like terracotta, things like the most ancient of the ceramics that we found is 18,000 years old, and that's pretty much kind of earthenware. Stoneware is um, fired at a slightly higher temperature, 1100 to 1300. Firing time also goes into this, and composition also goes into this. Porcelain, if you have kaolinite and you get it really, really, really hot, you essentially almost turn it into a glass. And, that's where we get the finest porcelain from. Right. I think one of the reasons I enjoy this stuff, my family history, my grandparents and before are from the Midlands in England, like the Stoke area, and they were all employed by the potteries. My grandfather was a kilnsman. His father was a kilnsman. His brothers were kilnsmen. Basically firing things was something they loved to do. Um, and my grandmother would have been one of the people who did the painting on all the ceramics. I think they worked for Royal Albert and places like that. All right. So yeah, so back to what they were doing with the silicon carbide. So if you have reducing conditions and can get the copper plus oxide, um, and what you can get this copper red, or I didn't know this before looking on Wiki, sang de boeuf, which means blood of beef, type glaze. And here's an example that it was on the Wiki page, but it's basically from the Metropolitan Museum of Art. Um, and it's a um, copper glaze, but it's not the blue copper that we have seen before. And it makes sense. Cuprite, Cu2O. This is copper 1 plus. Oxygen likes to be 2 minus, so it takes two of the copper pluses to balance out the 2 minus charge on that oxygen. And it's a beautiful red sorts of mineral, right? Let's see. I am going to give you those. In fact, there were a couple of other links that I had that I um, should have not talked through. So I put those in. This oxidizing and reducing conditions to give you different colors um, on art, on ceramics, and specifically, it goes back a long time. So, obviously, cave drawings are not baked on in a kiln or anything like that. But, ochre, red ochre is hematite. The black colors that you get can be magnetite. Those are different forms of iron oxides, right? Um, and in fact, Greeks took advantage of this. They figured out how to control magnetite, which is Fe3O4 versus Fe2O3, the regular iron oxide rust. Give you the links to these guys. This is from the British Museum. So, essentially, to make this sort of thing, you make a clay pot and you paint the figures on it with a slip. That's basically dilute clay that has a slightly larger particle size. You scratch details in, fire at 800 degrees, and the slip here, um, basically has iron in it, and you let it have as much oxygen as it wants, and then you get the color there. Um, and you then because you've painted parts of it and you have left other parts of it exposed, there's a difference there. The parts that are painted are going to stay a certain color. The parts that are exposed, when you fire it at 950 degrees with green wood, you get a lot of carbon monoxide instead of carbon dioxide. That ends up being enough of a reducing agent that you can turn some of the iron oxide into magnetite, Fe3O4. Um, and that magnetite's black. So this control over the atmosphere in the kiln and the temperature of the kiln allows you to, you know, uh, choose the colors that are going to show up. Because obviously you can't like paint something on, like if you can use indigo to make this blue. Indigo is an organic compound. It does not survive at 1200 or 950 degrees, right? So um, one more example of this, um, the siren vase, not phase. I did not go through a siren phase. Right, so it's more same sort of technique, a little bit more advanced. It had three stages with different patterns of and different slips used. And again, it's hematite versus magnetite. So I bring that up because there is a parallel there between the different oxidation states of the iron in hematite and magnetite versus the what you see with minerals like cooperite and azurite, the red and green, I'm sorry, the red and blue states of copper. Yeah, this one's a beautiful one. Right. Backslash next. So what did the students think? It's Journal of Chemical Education. They are going to include the voices of the students. Um, you know, you the orange and green are strongly agree and agree. Um, the somewhat agree is yellow. Disagree and strongly disagree, you can't even see. Right? So over a few years of running this program, I left this lab with a greater understanding of the dynamics of ceramics and glazes. This lab enhanced and complemented the course material. This lab experience demonstrated to me how chemistry concepts find practical application in the realm of art. These statements students agree with. One thing, oh, I don't have a, oh, let me scroll back up. Let me put this back here. One thing that you may not know, little secret, is that supplementary material is usually not behind a paywall. So in this case, the background material, the lesson plan, and pictures of the analytical data is available. You don't need, it's not, the supplementary material is not covered by paywall, so you can get at that stuff. You would have to go to the link I've just put in and, navigate to the supplementary material, but there's a wealth of stuff there. Okay, keeping an eye on the time. Summary. This is part of a larger body of work from this lab. Um, and they used about 4 semesters to look at this um, particular type of study, very very well received. And one nice thing is that they could use the microwave kilns, which would be more available to a broader array of institutions than the furnaces they used, and they got consistently positive feedback from students. Hey, these are my co-authors currently, all 4 of them, so you can see these guys. um, Quick second paper. Basically, JChem people publish um, from a lot of different institutions. Christopher R. Reinal from the Thatcher School, Ojai, California. This is part of a series of papers that explores teaching tools for the high school kind of non-science majors. And it's actually looking at the cultural heritage science open source. So CHSOS, right? Um, I've got yeah, pop the link in there. Um, you know, not everybody has access um, to high-tech tools. Um, it's getting better though. Here's another paper. Um, this is relevant, but it's the only slide on this paper. With 3D printing, you can turn a smartphone into a spectrometer. And here's how you do it, essentially. And there's a whole bunch of papers that are on this sort of thing. So, this actually means that um, um, high school use of like visible UV vis data um, is something that's within grasp for students, right? And just kind of going over what they did in this paper for some of their things was imported into a program called Logger Pro, and that's from Vernier Instruments. We have it in our labs. It is widely used with spectrophotometers designed for classroom use. Vernier sells to high schools and middle schools, I guess, and universities. And so in red here is a quote. They can use this data to explore how chemical content knowledge and analytical instrumentation can be utilized in the characterization and authentication of works in art and cultural heritage objects. He used this in his class for several case studies, and I'm only really going to chat about one. Um, he was able to take his data into Logger Pro. Here's X-ray data for the pigment Naples yellow. It's one of the pigments in the database, and for the um, background, the supports, like what the um, pigment was painted on. The Raman spectrum is actually in the next slide. Um, and essentially looking at this Naples yellow um, at 4 different laser wavelengths. Because if you have happen to have a Raman spectrometer and your laser is different than the one in the literature, then it's not an apples to apples comparison. So it's nice to have all of these lasers. Um, Maybe in a future talk, I'll talk a little bit more about Raman. It's a vibrational technique. It basically tells you almost the same information that infrared spectroscopy tells you. Um, so essentially, and I'm going to be very careful with time here because I know we have a thing happening at noon SLT. Um, Essentially, what they did is looked at a video on um, art forgery. The particular video is linked there. I've given you the YouTube to it. And they were looking at whether a art piece of art that was supposed to be by Chagall was actually by Chagall. So they followed the team on the TV show through the various chemical analyses they did, and then paused the video right before doing the comparison of the Raman spectrum of the pigments used. And, essentially, they found this phthalocyanine blue in the painting, but that is not a dye that was available to Chagall. So confirming that the thing was fake. Right. So this was something that students could draw attention or could draw conclusions of, based on looking at the actual data that was available to them. So yeah, so this is just the link to the actual tool, the open source um, um, cultural heritage. And, this is a typical spectrum. It's basically UV-Vis spectrum of, um, indigo, because I like indigo, under different conditions, the powder, the egg tempera, fresco, linseed soil. So you can actually compare how the spectra change under different conditions so that, if you're an art conservator, you can actually make the appropriate match. So yeah, so kind of concluding here, while it's productive to use a search site or AI summaries for literature for work, you lose the ability to come up with something refreshing, right? And so I find for teachers, it's important to have a broader perspective. So wading through tables of contents per week, it's fine. It ends up being quite rewarding. And this is like only a tiny sample of some fun content I've been able to gather over the years. So I'm hoping in some future talks I'll dig more deeply. Some acknowledgments. NSF has been very kind. My collaborator George has been very kind. All the people at SIUE have been kind, and especially you guys for coming and supporting Science Circle in here and outside of Second Life. And I actually have, I'm not going to talk about them, but I'm going to give you the links to open access articles, one on potions, poisons, and perfumes, and the second one um, on mineralized remains as adjacent proxy for radiocarbon dating, which is basically if you have an artifact, but you've got artifact in some layer of soil and you've got some of the mineralized soil that's next to it, you can date the mineralized soil to date the artifact. So again, this is one's open source. So that's what I've got for today. And yeah, no more slides. And I actually stayed on time for once, so I'm that's quite the accomplishment for me. All right, so thank you. Any questions? I don't think I caught everything that was going on in the nearby chat. You're welcome. You're welcome. Yeah, these are not hard to put put together because I had read the articles. I did have to refresh my memory, and the ACS actually makes the figures easily available to talk about on the slides.